Hello and welcome to this clip reviewing the combustion of alkanes. As always, your independent study and notes need to be in front of you to make the best use of this clip because it's designed to support the work that you've done. So the two main thrusts of the clip are to look at how to construct a combustion equation, in addition to having a look at the implications of complete or incomplete combustion. So in general terms, combustion is a process by which a substance burns in oxygen. And although obviously you can take a gas jar of oxygen and combust a substance in that gas jar of oxygen, the reaction is generally assumed to be happening using oxygen in the air. And obviously because oxygen is combining with the substance, it can also be regarded as a form of oxidation. So as you'd expect, the substance being combusted is called a fuel, and the reaction products are called combustion products. So the process is usually carried out deliberately under controlled conditions in a domestic appliance like a cooker or boiler, the point of which is to try and get energy in the form of heat. And all combustion reactions release energy and are as such called exothermic, a word you might have come across before you started A-level chemistry. So when we study combustion chemistry in detail, most of it involves the combustion of organic compounds as the fuel. So the carbon in the organic compound is oxidized to CO2 or CO, and the hydrogen present is converted to water. And whilst complete combustion is assumed to mean that all the carbon is fully oxidized to CO2, but incomplete combustion means that carbon is only partially oxidized, giving off the toxic carbon monoxide, or it might not even be oxidized at all, being released as pure solid carbon or soot. So when we get incomplete combustion, the products are assumed to contain at least some carbon monoxide gas, but it's hard to tell how much carbon has become soot and how much has actually been oxidized partially to CO. So because carbon monoxide is odorless, tasteless and colourless as well as being highly toxic, there's a number of deaths unfortunately per year due to faulty domestic appliances not burning their fuel properly. So on the left is a battery operated carbon monoxide detector that you can buy for about £10. In most hardware stores it's recommended by the fire services and emergency services that every house has one. This one's attached to the ceiling in my kitchen, and the domestic boiler in our house has a built-in monitor to show if the fuel is burning properly. What you can also see in other older domestic boilers is if the flame is blue, then that means that the fuel is burning properly. If it goes yellow or smoky, that means it's giving off carbon monoxide and soot. So when you construct a combustion equation, you always assume that you're burning 1 mole of fuel. And we'll start by doing complete combustion, which is, like I said earlier, the combustion product is always CO2. So you begin by writing out the fuel together with oxygen, that's oxygen gas, and of course I was just testing out there. I mean, I wouldn't have done anything like forgetting state symbols, no, never. Seriously though, you allow a little bit of space to balance the oxygen so you can see between the plus and the O2. I've left a bit of space because I need to put a balancing number in, possibly, at some point when I finish the equation. So I put in my carbon dioxide and my water. I now need to balance for carbon, but I can already see that there's 1 carbon on the left and 1 carbon on the right, so that's done already. So the next thing to do is to balance for hydrogen. Now on the left I've got 4 hydrogens, and on the right I've got 2. That means I've got 2 moles of water being produced from 1 mole of methane. And finally I can balance for oxygen. So on the right hand side I've got 4 oxygens in total, 2 from 1 carbon dioxide and 2 from 2 moles of water. So that means I need 2 moles of oxygen gas on the left. And that's us done. Now, that was for complete combustion. Let's now do it for incomplete combustion. So this time we're going to use a different fuel, just to mix things up a bit. Propane is used in barbecues. So this time the only carbon combustion product is CO. So I just wanted to point out before we start that because of the exothermic nature of combustion that we talked about earlier, the water will always come off as a gas. That's different to when we do the equation for standard combustion, which comes up later in the course. Standard combustion happens when everything is in its standard states. And water is not in its standard state as a gas, obviously, but in reality, if you burn some propane, you're not going to get a spray of droplets of water being produced from the hydrogen. It'll come off as steam or just as water vapour, because the actual burning process will take place at greater than 100 degrees Celsius. So looking at this one, you can see straight away that it's not balanced. So if we go back to our instructions at the beginning, when we did methane, the first thing to do is to balance for carbon. And now what we've got to do is balance for hydrogen. And finally, like we did before, we've got to balance for oxygen. So if we count the number of oxygen atoms that are contained in the combustion products, that is the carbon monoxide and the water, you can see that there's actually 7 oxygens. Now that begs the obvious question. You've got 7 oxygen atoms, but the oxygen is coming in the form of O2. How do you get O2 into 7? This is where you can use a little trick, and it's called using an improper fraction. Now we're allowed to do this in chemistry because we said at the beginning that we were assuming that you're burning 1 mole of fuel. And the reason for that is sometimes we need to measure energy per mole of fuel combusted. Let's say that we're analysing 2 different fuels. So for that reason we have to use improper fractions. You could use a decimal if you wanted, 3.5. But let's imagine that you were not going to do that, and in your mind what you wanted to do is double everything up. The problem with doing that in order to make the numbers whole is that you're now not burning 1 mole of fuel. And the difficulty here is this now means that you're combusting 2 moles of fuel. You can't use the energy from this particular equation because it would be the energy for 2 moles of propane being burnt, not 1 mole of propane being burnt. So it's important to try to stick to 1 mole of fuel. So sometimes what they might do is refer to a solid product in the question. What do you do in that situation? Well, obviously then you can assume that it's carbon. So what you do in this particular case is put in the 3 carbons as your solid product. So this would be propane, where the carbon hasn't actually burnt at all. Only the hydrogen is burnt to make oxygen. So if you look at the number of oxygens that you've got on the right hand side, obviously now you only need 2 moles of oxygen molecules on the left hand side, so it's a lot less required. So let's now summarise what we've talked about so far. So combustion is the reaction of a substance with oxygen from the air. A fuel is a substance which is burned specifically for the purpose of obtaining energy from the reaction. All combustions are exothermic and give out energy. When combusting organic compounds, the products of incomplete combustion, such as carbon monoxide, are very toxic and dangerous. Complete combustion always produces CO2 as the carbon combustion product. So let's now summarise very briefly the technique for writing a combustion equation. The first thing to do is to read the question to see whether it's complete or incomplete combustion you're supposed to write the equation for. So complete combustion gives carbon dioxide and water, whereas incomplete combustion always gives water but may give carbon as a solid or carbon monoxide gas as the combustion products. You make sure that you combust 1 mole of the fuel molecule, so your alkane or alkene, for example. And finally, you balance for carbon by putting in the correct number of CO2 molecules on the right hand side, hydrogen by balancing the number of H2O molecules on the right hand side, and then finally oxygen, and you can use decimals or improper fractions if necessary. So that takes us to our end of our review of combustion of alkanes and some of their implications. Hopefully it's been a fairly useful introduction. As I always say, it's a good idea to now go away and practice some examples to make yourself comfortable with this. So until next time, thanks a lot and see you soon.